Okay, the recording is starting now. And screen sharing should be coming through in a moment. There we go. All right, thank you, ladies and gentlemen. So we'll begin with the last bit of content for the course. The remainder of the lectures this week and tutorials will be taken up with past papers, and then also past exam papers, and also we will have some video past paper work-throughs uploaded even after the end of the term, just so that you can have more practice and more things to compare what you've done with. Then also the results for semester test 2 will be available this week, but with projects day it'll probably be later in the week. And then obviously as soon as semester test 2's results are out, on Friday your VPL supplementary exercises are due. So on Friday we will calculate and release provisional semester marks on the basis of your semester test 2 and your practical marks and semester test 1. Obviously you can then query those still, so those marks can change, but your semester test 2 results should be out at the end of the week, as well as your provisional semester mark and exam entrance and so on. Just see if there's any questions in that regard. That I still don't have a final answer for, so my suggestion is to study as though it's not an open book. I know that semester test 1 was, but we don't have a final word on it. Obviously all the questions are written to be applied, but yeah, study as if it weren't. Don't assume anything. So then if it turns out to be, wonderful, and if it turns out not to be, you're prepared. So please bear that in mind. All right. Okay, let's get this done. And then, all right, sorting, searching, and algorithmic analysis. So this could technically be part of Computer Science 1A, to be honest. But the reason it's with Computer Science 1B is because Computer Science 1A doesn't have a theory exam, whereas Computer Science 1B does. And this is partially quite a theoretical section. So really, it would fall under Computer Science 1A if it weren't for that exam limitation. So basically, what we're going to take a look at, and you will get a question about this in the exam. There's always a 10-mark question about it. And it's not that difficult. So once you know how to do them, you can think of those as 10 marks, or maybe let's say you get 8 or so, but you'll get most of the marks, and it's an easy way to rack up the points you need to pass or get that distinction or whatever it is you need. But the basic idea is that we'd like to look at analyzing the running time of a computer program in a way that's separated from the machine that it's actually running on, and basically to analyze it from first principles and see if we can compare two algorithms in terms of their expected running time without actually running them. So that taps into a field of mathematics called computational complexity, and then we'll take a look at some of the sorting algorithms and searching algorithms that exist through that lens. You won't be asked actually to implement a sorting algorithm. Some years there have been. It's definitely in the scope of the exam, and maybe it could be in the SIC test or the special SSA for the exam. I can't say for that, but certainly it's not the main focus, implementing a sorting algorithm, but it has been asked. Searching algorithms, particularly the linear searching ones, you know already through linked lists. We've already looked at that. So the more advanced searching algorithm we'll take a look at is really just to contrast it with linear search, so you can see the impact on computational complexity certain decisions can make. Right, so let's look at analyzing algorithms. How fast is a given algorithm, and how do you measure it? So would you measure it in seconds, milliseconds, nanoseconds, minutes, years, months, days? It really does depend what the algorithm is doing, and in any case, that's not really measuring the algorithm in its sort of abstract mathematical sense. You're just measuring a particular run of the algorithm, because obviously if you run a complex algorithm on a potato, it's not going to run very well. So the effect of the underlying hardware doesn't really have anything to do with how good the algorithm is. You could write this amazing code, and if it gets run on poor hardware, then it will look like it's performing poorly, but it's got nothing to do with the quality of the algorithm. And then again, these days algorithms tend to run in a distributed way with multiple copies of them running on different machines. Especially imagine if you run anything that runs in the browser on the web, that stuff gets distributed to everyone's computer who connects to your website and runs there. So algorithms will run on many machines, not just on the one machine you developed it on. So it's nice to be able to express the complexity of an algorithm in terms of its time in some way that's independent of the system specifications of the machine you're running it on. So how can you compare two algorithms? Well, algorithms, obviously you can run them multiple times on different hardware and see which one tends to do better. And in fact, running the same algorithm on multiple different bits of hardware is used not so much to measure the algorithm as it is to measure the hardware. So if you've got a known complexity algorithm and you run it on multiple machines and keep everything else the same, the machine that it consistently does better or worse on, you could say that the problem then is an issue with the hardware. So they call that benchmarking. Presumably it's got something to do with some physical manufacturing process with literal marks on benches, but the name's been inherited, and we use it now to refer to sort of stress testing hardware by running algorithms, the same algorithm on different hardware with the same data. All right, but let's say you've got two separate computers and they're each running different sorting algorithms on collections of the same size. So if computer A completes its sorting in 10 seconds, while computer B completes it in only 5 seconds, it would be incorrect to assume that B is superior to A. Because, like I said, the computer might have different hardware resources, and some algorithms perform much worse as the problem size gets bigger. We just said the problem size was the same. We didn't say what it was. So some algorithms work fine on small problems, but really get bad as the problem size increases. So it would be useful to be able to compare the performance of those two algorithms from first principles. So what governs the execution time of an algorithm? Well, almost always it's related to the input size, which we're going to call n. So if you're thinking about processing arrays or vectors or lists or whatever, it'll take much longer to process a list of 10,000 entries than to process a list of 10 entries. So n, the size of the list in that case, is the factor that dominates how long something is going to take. So we'd like to express the running time of an algorithm as a mathematical function, which we'll call t, or the time, which is a function of the input size, so t of n. So basically, we'd like to come up with some expression that will give us a sense of how complex the running time is going to be. So sometimes an algorithm will perform better or worse on different inputs of the same size. So even if you've got let's say a list and you're searching for a particular item, and the lists are the same size, but one of the lists happens to literally have the item you're looking for as the first entry, it'll complete really, really quickly, instantly almost. So the problem size isn't necessarily the only factor, but we're talking about kind of in the average case, what's going to be the most dominant factor. So in fact, we're not really that interested in the average case, although there are formulas for it. Computer programmers are actually kind of pessimistic and pragmatic, practical. So to be honest, which is more important? The best possible case of the algorithm completing, i.e. your answer is the first element, the average case, or if you're designing for systems that need to run a lot and under sort of unsupervised conditions, or just you can't spend all your time sort of babying them, you probably should really focus more on the worst case scenario. And there is a mathematical expression for the worst case performance of an algorithm, which is called big O notation. It's actually, technically speaking, an omicron, not a regular O, but we just call it big O. And basically, if you take big O of a function, it will tell you which part of a polynomial, it'll tell you which part of that polynomial is going to make things worse, i.e. make the value of the function go up the fastest. So if you take a look at this particular polynomial over here, which component is going to make this which term is going to make this get worse fastest? you can see over there we've got a huge coefficient of the term n2 and small coefficient of the term n to the 1. And 5 obviously is the coefficient of n to the 0. But which of these is actually the biggest culprit over all possible values of n? And you'll see that while early on that second term is going to have a huge impact because of that massive coefficient, very quickly the term n to the 3 is going to have the biggest effect because that cubing will have much greater impact as n tends towards infinity than any fixed value coefficient possibly could have. So what the big O operator does, in a sense, is it takes a polynomial and it just simply throws away the coefficient and gives you the term with the highest exponent in it. And that term is the one that is the most important. So that's what we actually use when we're talking about comparing algorithms. We look at their big O value, and if the exponent is higher between two big O values, we know that that one will perform much worse most of the time. So that's the notation we're going to use. So there's ways in which you can formally state it, but we're not going to worry too much about it. But that's basically just giving you a discussion of why the n to the 4 term will dominate the value far more than anything else. You could, of course, prove it to yourself by plotting values and seeing when the curve overtakes the other and how it will stay above, dominate the other terms from that point onwards. But basically what you need to know is how to apply it, and basically it just means look for the term with the highest exponent of the variable and chuck the coefficient away, and that's your end result, which is all well and good. But how do we actually get that coefficient, get that function in terms of n? So let me just see if there's been any questions while I've asked. So that's a good question. So the philosophy at UJ is for computers, each subject to teach to its speciality. So rather than having a computer science specific for a mathematics specific for computer science, you do the general mathematics along with everyone else. Because, well, that's basically just been the philosophy. We'd rather have you come out with a full, proper mathematics education rather than just one that's only focusing on the things that are relevant to computer science. Mathematics is useful to you more than just as it relates to computer science. It makes you a much better problem solver and a much more well-rounded person. But there are particular branches of mathematics that are especially useful for computer science, such as discrete maths. And we do allow students in their second year to take discrete mathematics instead of calculus because that is useful. But we don't offer special mathematics for computer scientists because we do want you to have that proper grounding. But the mathematics you do in the normal maths 1 and 2 is super useful. If you started working with vectors or you started working with matrices, vectors, matrices, and graphs are the heart of almost all computer science algorithms. So and that gets taught in the normal maths modules. And that, if you can pay attention to vector mathematics, discrete matrix mathematics, the two obviously very closely related, and graph theory, you will have a very good grounding for the computer science algorithms that use that. All right, so let's carry on. So if we take a look here at this, how are we going to get a coefficient, a function in terms of n that describes this? So the way in which we will do it is we will count operations. Now, basically, the code you see is actually broken down into a lot of smaller steps by the compiler. The actual instruction set for your CPU doesn't understand what an integer is and doesn't understand what assignment is and so on. But you know, this particular expression is one statement in C++, but it's actually will be several machine code operations, but that doesn't matter. What does matter is you pick your operations and you count them. Some will be more expensive for the computer to do than others. For example, multiplying by a real number is a very expensive operation for the computer to do, whereas multiplying by an integer is very cheap. But it doesn't matter because we're looking for the worst case scenario here. So what we're going to do is we're simply going to count the operations and then assume that the worst, or that they're all as bad as the worst of them. And then we can have a count for the scenarios here. So we could say that declaring an integer is one operation and assigning a value is another. So that would then be 1, 2, 3, 4, 5, 6. Same for Booleans, 7, 8. Same for doubles, 9, 10. And then over here, we could say evaluating the if is an operation, 1, and then the ors as well, 2, 3. And then assigning 4, 5, 6. Sorry, I restarted my count, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now you might say, wait, but the compiler will probably optimize the bitwise, the logical OR operations. As soon as it knows that's true, it can skip the other two. Possible, but again, what if it doesn't? All we're saying is we want the worst case scenario here. So if you've got a constant time algorithm, an algorithm with no loops or recursion or anything like that, you need to find the longest possible path through the program and count those operations along that path. And it doesn't really matter if you pick exactly the same operations as someone else, as long as you count operations that occur along the entire path. Because let's say someone here forgot that declaring or allocating space for the integer also takes time, and they only counted the assignments. Then you get 1, 2, 3, 4, 5. Let's say they even forgot to count the other stuff, 6. So you're going to have 6 operations as opposed to 15 or 16. You'll still see that as long as they all occurred along the branches, you'll get the same result at the end of the day. So this is how your answers to these questions will look like. You must write them out fully because you get marks for the sort of steps. Don't just jump to the answer. For most of them, you'll be able to immediately jump to the answer. Then you'll get 1 mark. You need to work your way to that point. So for example, here, you pick the operations you're counting, tell us what they are, right? And you say that they're a fair measure of complexity. So what that basically means is there's no hidden loops or anything weird inside them. They're going to boil down to a fixed number of machine code operations. Whatever that number might be, we don't know. We don't know because the optimizer might even make them smaller, but it's a fixed number. There's no hidden depth to them. And then we can basically say that each operation will take the same amount of time. They won't. Some will be faster than others, but we'll just assume that whatever operation is the slowest, that's the speed they will all take. Then we need to decide what n is. So in this case, there isn't really a problem size, to be perfectly honest, because there's no real thing that can vary here. But we still need to declare that we're working with an n, and that n represents the problem size. Therefore, t of n represents the running time of the algorithm. Now we count this. It's really easy. So I got 12 that time. I must have not counted the ifs and stuff. I think I forgot to do that. Whatever. Doesn't really matter too much. You'll get some count of the operations along the path. And you just get that. You'll see what's the term of n that has the largest exponent here. That would be n to the 0. It's hiding there because n to the 0 is 1. So the final complexity of this algorithm is big O of 1. And we call big O of 1 operations constant time. And they're very nice because it doesn't matter how big your list is or how big your vector is or whatever it is. They always take the same amount of time. So if we're taking, for example, a look at the linked list, inserting at the head of a linked list is constant time because we don't have to loop through the linked list to find a place or whatever it is. All we need to do is create a new node, link that node to the head, adjust all the pointers, increment count, and we've added our linked list, our node to the head of the linked list. So it's a fixed number of steps. So big O of 1 is the best possible complexity we could get. Let's see if there's any further questions. Yeah, probably. And this is I really should have, and that's why my count that I did now was different to the other one. You should try and count as many as possible. But it isn't a crisis if you miss one, is what I'm saying. Because as long as you're counting the operations along the path, the big O operator will wipe them all out. So let's say we got 6 just by counting the assignments. Or let's say we got the 16 that I got just now. It'll still boil down to the same final complexity class answer because the big O operation doesn't care about the coefficients and it doesn't care about the constants. It only cares about the terms of n. And in this case, the only term of n is n to the 0. So big O of n to the 0, which is big O of 1. and that's our final answer. Okay, so let's say we're now doing an algorithm that's a little bit more complicated, one with a loop, an iterative algorithm. So this is a single loop, and we can see that it's a searching function, right? We're searching through an array to find some sort of target value, right? Otherwise, we just keep moving, count how many times it takes us to get to that position. But we might stop early because we might find the thing soon. But that's the worst case scenario. That's an optimistic case scenario, maybe average case, maybe best case scenario, we find it right away. So we're looking at the worst case scenario. So we need to basically look at the maximum number of times that the loops are going to loop around. We need to decide as well, which of these things controls the size of the problem? And that'll be the array length. So the array length is our problem size, it's n. So we need to count our operations as before, decide what they are, also decide what our problem size is, its array length, and then work out how we can get an expression in terms of n. So once again, we pick our operations and we count them. We say that they're a fair measure of complexity. They take the same amount of time. N is the problem size. Strictly speaking, now people who don't watch the lectures and who just skim through the notes are going to miss this. This would actually lose a mark now because it doesn't say what the problem size is, which variable or whatever controls it. In the previous one, it doesn't matter because there wasn't really a variable that controls anything. But here, I want you to also say in brackets or something, it's array length. That's what n is, the problem size. So now we can again say let t of n represent the running time of the algorithm. It contains a single loop. So what does that mean? It means we've got the operations outside the loop, and we've got in some kinds of loops we've got operations that only occur once in the loop head. This time we won't the loop condition. And then we've got the operations that occur inside the loop, and they can occur as many times as the loop iterates. So basically, we've got the operations outside the loop plus the maximum number of operations inside the loop, which will be when the loop runs for its longest possible duration. So we'll have some constant value for the outside operations, inside the loop, evaluating the guard conditions and the loop body, and then the maximum number of times the loop is going to run, and that's the n we decided on. So we multiply and add and get our final answer, 7n plus 2, and then we apply the big O operator to it. So the n is the biggest term there, that's n to the 1. So throw away the coefficient, throw away the constants, and we're left with just big O of n. This is what we call a linear time algorithm. So it will grow in exactly the same rate in terms of its complexity as the problem size gets bigger. If the array is one element larger, then there'll be one more iteration of the loop. So it grows very predictably with the size of the array length and very smoothly. Now we could have situations where we've got nested loops, and there's different ways of handling it, and you'll do more complexity analysis in Computer Science 3A in much more detail. So this is just the basic idea that you need to understand for this. So for this, we're going to make a simplifying assumption that if we've got nested loops, they might have two different number of loop control variables that govern them. In this case, I've made sure that the loop control variable is some value n, maybe it's a constant or something defined elsewhere, but it's the same one here. However, it could be different. You could have rows and columns and int rows and int columns governing them. However, think of it like this. Either your array is square, in which rows and columns are the same, or either rows or columns is larger. So since we're just purely worried about the worst case analysis, we'll just say that it's going to be the larger of n1 of rows and columns. So in this one, it doesn't matter. I've explicitly made them the same. But how do we solve this? Well, same situation. We've got the values outside, the operations outside the loop. We've got the operations inside the conditions for the loop. Some only occur once, like that assignment there and there. Others occur every time the loop loops. And then the inner loop will occur one time for every iteration of the outer loop. So if this occurs n times, this is going to, if this occurs n times, the inner loop is going to occur n times. So again, we just spell it out. The operations, list them. It doesn't matter, as I said, as long as they occur throughout the entire path of the code. That's all we really worry about. Take the same amount of time. N is the problem size. In this case, there literally is a identifier called n, so we can just say that. We don't have to clarify any further. we can let T of n represent the running time of the algorithm and contain loop. Therefore, it's the total number of operations in the outside loop plus the maximum number of operations inside both loops. So we count them up, count our outside operations, our innermost loop, count that up, get something in terms of n. Outer loop, same story, something in terms of n again. But now we'll see that the inner loop occurs as many times as is necessary based on how the outer loop occurs. So we'll have an n multiplied by n, giving us 3n squared plus some constant, which in that case, if we apply the big O operator to it, we're going to be left with big O of n squared, throw away the coefficient and the constants, and that's our final answer. So that's a big O of n squared example. Now here, as I said, what happens if they've got different bounds? Just assume that one of the two bounds is larger and carry on, and tell us what your problem sizes are. And then it's exactly the same story as before, obviously with different numbers, count it all up, and you'll be left with your complexity there. Now there's more complex things than just single or doubly nested loops or singly nested loops. You could of course have 3, 4, 5, or in horrible, you could have the loops n times. But basically, you could have n levels of nesting. You could have some sort of process that will basically loop over the collection based on how big the collection is, and process each element on the basis of how many elements there are in total. So it is possible to have big O of n or big O of n to some expression containing n, and you won't do that in Computer Science 1, but you could have things like that in Computer Science 3A. So for now, we just keep it simple, just to get the basic idea across. So that's a doubly nested loop. Let's see if there's any questions. You can easily extend the idea to arbitrary levels of nesting. So if you're doing, it depends on which degree you're taking. Remember, so some of the degrees will have applied maths in it, and applied maths can be useful. So if you're in a degree that allows you a choice of modules and you've got the prerequisites for applied maths 2B, you can take applied maths 2B. For the, let's say, computer science and information technology, not every person studying information technology will want to study applied maths as well as the maths we require them to do. So it all depends on what degree program you're doing, whether it has electives, and then whether you've met the prerequisites for that. So yeah, applied maths will study this, because remember, computer science is a branch of applied mathematics. So this has got actually technically nothing to do with computers per se. This is actually analysis of functions. We're basically looking at which functions dominate other functions, i.e. Consistently produce values that are higher than the values of another function over what period they do it. So we look at it in the context of applying it to analyzing source code, but it's actually its own branch of applied mathematics. That you could be looking at, you could be looking at just purely the functions in their own pure mathematical sense with no connection to computer code in any way. And if that interests you, then of course, take applied maths if you have the space to do it in your degree and you've met the prerequisites. But most computer scientists will just be interested and be able, well, let's say in this case, IT professionals will just be interested in getting a sense of how large one algorithm is, or how poorly one algorithm performs in the worst case compared to another. But yes, it can go much, 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 much further. Right, we've looked at code without any loops. We've looked at codes with single loops. We've looked at codes with double loops, and theoretically you could extend that to 3 or 4 loops. So I mean, like, we wouldn't make you extend it to n or some weird expression in terms of n, but if we gave you something with 3 levels of nesting, you should be able to apply the same idea that you've seen here, and you'd be able to see that you'd need to do this for inner, middle, and outer loop, and eventually you would get some expression in terms of n cubed. There might be another term with n squared in it, and then 3, but you only care about the highest one, so your result there would be big O of n cubed for a triply nested structure, like what you had with the point cloud and so on, the vector fields and so on, or the cube stuff. So that's a possibility. What happens if there's no obvious immediate loop? So for example, if you've got recursion, at the end of the day, recursion is actually just an alternative way of expressing loops. There's nothing that you can code with recursion that you can't code with loops, and vice versa. There are some programming languages that don't have loops at all. Some of the pure functional programming languages, you don't have variables you can modify. You only have mathematical values, but you can still define repetition through the use of recursion. So they're equivalent in their expressiveness. So let's take a look over here. If we were calculating trying to raise one number to another number's exponents, so calculate the power, you can do that through repeated multiplication. You could do it with a for loop, or you could do it recursively. So basically what we've got is simply a count of the number of times we have left to recurse. We subtract that at each point, and we simply multiply by our base x, and then that will wind up occurring n times until eventually it hits the base case, returns 1 multiplied by everything value, and we've got a recursive exponentiation function. Clearly, this isn't a constant time function, because as n gets bigger, it's going to recurse more and more and more and more. So we apply basically the same logic as we did with loops, but you could literally just do it the same way as you did with loops, or you could basically establish the sort of pattern that develops as n gets bigger. So it's a recursive function. So you don't even need to count all the operations here. You could literally say the one that definitely occurs all the time in the recursive functions, except in the base case, is the actual act of calling a function recursively. So as an example here, we're just going to call the recursive function call as a fair measure of the complexity of this algorithm, because the base case will always be constant time, so it won't change the final result. Each operation takes the same amount of time, so basically each recursive function call we say is going to take the same amount of time, and that's not necessarily true in practice, because you could have your program being interrupted by the virus scanner, or you could have the need to clear the cache memory because you've used up all the cache memory because you've been calling things on the stack. You've got lots of things that could change. Cache coherence might not be so good. Whatever, there's lots of things that could vary, but it's good enough to get a sense of what's going on. So we've got n, which is our literal parameter n, represents the problem size. And there are other assumptions that maybe you might know about a particular algorithm you can put in. So for example, this algorithm is only going to work for positive integers. So you can put that in as part of your assumptions. Then once more, let T of n represent the running time of the algorithm. It is a recursive function. So basically it's going to be the operations in the base case plus the operations in the recursive case as many times as the recursion happens. So in the base case, since all we're doing is counting recursive function calls, we can say that there's no function calls there. And then as we increase n, what happens? Well, there's one recursive call when n is 1, 2 recursive calls when n is 2, 3 recursive calls when n is 3. So that means when we substitute n in, we will get n recursive calls. So we can say that the algorithm has complexity big O of n. You could have still done it like a loop, but you have other options as well. Right, let's see if there's any further questions. So that's a great question. I'm happy to answer that. So I did the undergraduate mathematics 1 and 2 like we had to, because I did the BSc IT degree. Back when I did the BSc IT degree, so okay, I'll answer the second question. It's a good one in a moment. Just give me a second. The BSc IT degree was a little different when I did it. We had to do math stats as well. So I also did 1 year of mathematical statistics. Now, we had the choice back then as well, whether we could take discrete mathematics or advanced calculus. And I took advanced calculus, and I enjoyed it, but I will 100% tell you that it's not as useful as taking the discrete mathematics. So from a computer science point of view. So anything like, combinatorics and stuff like that, which we also did in stats, is super useful in computer science. And it's a waste. I would say if I took the calculus, it has been a little useful, but the discrete maths is better aligned to computer science. So if you have a choice, and it depends exactly on what degree you're taking, some of them do offer the choice, some don't, then take discrete maths. If you do have the choice, if you don't have the choice, don't worry about it. The calculus was still very interesting. Of course, some of the degrees only require 1 year of maths. It all depends, because that's the whole point, is that not everyone in doing computer science 1 is doing BSc IT or even doing a BSc at all. Anyone can take computer science 1, just like anyone can take the math modules. It's not tied to a particular degree, but that was my personal experience. And then, no, the notes haven't been uploaded to yt5s yet because there's the SIG test was running this morning. So the notes will be restored to their original state today, and then those notes will be uploaded. But I'll tell you what, I'll upload these notes to Discord so you can get them now if you really want to. So good question. All right, so the last thing here, just less important in the sense you won't actually be asked to write any code like this, but it's useful to know. You've already done the linear searches with linked lists and with arrays when you've searched for something in an array, but it's just a continuation of the discussion before. You won't need to know the proofs of the complexities of these algorithms either. So sorting. There's different kinds of sorting algorithms that exist, and some are better than others in some cases and worse in others. So ways in which you can compare sorting algorithms is their complexity class, which we've seen already. And you can do that by measuring things like the comparisons and the swaps or whatever. You can take a look at how much memory the algorithm uses. An in-place algorithm won't use an amount of extra memory that's related to the problem size. It might use a fixed amount of extra memory while it's doing a loop or something, but it won't grow with the size of the problem. Whereas non-in-place algorithms will grow with the size of the problem in terms of their memory usage. They can be built in recursion or loops, and they can be stable or unstable. Now, what that means is if you've got items with the same value, do they wind up in the same relative positions after the sort? So it's basically just about handling things that are tied. You were sorting all the students based on their marks. Now, a whole bunch of people might get 90%, right? And let's say the original list was ordered based on their surname. Will the people who all get the same mark, let's say 90%, still be ordered in terms of their surname once the sorting has done, or will that information get lost due to the sorting? Obviously, people with different marks will have will be in different places, but the people who have the same sorted value, will their order be preserved after the sort? Exactly what comparison criteria you're using, and a lot of sophisticated sorting algorithms are built upon the simpler ones, the variations on it. So you can take a look at there. So here we have insertion sorts. Basically, you split a list into two portions, the sorted and unsorted portion, and you basically grow the sorted portion by successively placing items into their correct position in the sorted portion. So originally, only the first item is sorted because it's one item by itself, and the rest of the list is unsorted. You then find the next item and place it in its correct position in the sorted thing. So basically, it'll go either before or after that single item. Then you grow the sorted portion again and again and again, continuously inserting the new item that you're considering into its correct position in the sorted list until eventually the entire list is sorted. Most of these will be pretty garbage in terms of their performance. You can see worst case performance here, big O of n squared, but it is in place, it is iterative, and it is stable. There's an implementation for it if you do want one. Then we've got selection sort, which is similar. Basically, you find the smallest item in the entire list is going to be first. So you can find the smallest item first and put it in the first position by swapping it with whatever was in the first position. Then you can find the second smallest item and put that in the second position. Then the third smallest item and put that in the third position, and so on until you're done. Again, it's going to also be big O of n squared, which is not great. Most of these aren't going to be very efficient because they're very simple algorithms. Don't have to learn this proof, but it's big O of n squared. Now here's the first algorithm which is going to give better performance. It's called merge sort. And basically it's built on the observation that if you've got a bunch of already sorted lists and you want to merge them into a completely sorted big list, it's easy to do because they're already partially sorted. You just take items, let's say you've got two sublists, you simply keep taking items from the one as long as it's smaller than the top item on the other, and then you switch over to the other pile as long as its values are less than the ones on the first pile, and you just basically keep doing that until you've merged the list. So merging pre-sorted lists is easy. Also, if you've got a list of 2 items, sorting that is trivial because it's just 2 items. So what merge sort does is it splits your big list up recursively into smaller and smaller and smaller lists until they're eventually only 2 items each. Then it sorts those sublists, and then the recursion unwinds until eventually you've sorted the entire list. So it's a bit more complicated, and we won't ask you to know the code. There's no point in asking people to memorize code in any case for things like that. So, but most of it's just about handling the different lists. The actual heart of the algorithm is here, where basically you sort the top half of the list, sort whatever falls in the middle of the list, and sort the top half of the list, recursively splitting them, because this merge sort will wind up calling itself merge sort, calls merge sort, merge sort calls merge sort, and then you've got your sublists generated by these 2 steps. You just combine all the sublists into a single list, giving you your final answer. So its performance is actually great. It's big O of n log n, which doesn't sound that great, but it's certainly much better than big O of n squared, because the logarithm is not going to grow as quickly as another term of n. So you're never going to find a sorting algorithm that's big O of n, but big O of n log n is really decent. It's higher than big O of n, but it's lower than big O of n squared. The only problem is that this uses a lot of memory. Why does it use a lot of memory? Because of all the recursion. Remember, every time you call a function recursively, you use up a little bit of extra memory. And basically, it needs to store all the copies of the partially sorted or partially split sublists on the stack as it recurses. So you're paying for speed in terms of memory. Here is one of the easiest, but also bad. But then again, if you're looking at only the worst case performance, it's as equally bad as the rest of them, but it's really bad all the time. It's that bad all the time. So people often consider this to be the worst of the real sorting algorithms that people learn about, as opposed to fake sorting algorithms. That I'll tell you about one in a moment. But basically, this bubble sort is a nice idea because it helps you understand the notion of what sortedness means. So when is a list sorted? It's sorted when the item that's further along in the list is greater than the item that's before it, right? And if it's not, swap it. So basically, all that bubble sort does is it repeatedly loops through the list again and again and again, checking that each item that comes after it is greater than or equal to that item itself. If it's not, it swaps it. So in this case, you don't need to show the equal because you do the action in the case of it not being equal. So if the thing is in the wrong place, i.e. at position I is smaller than at I plus 1, we'll put them in the right place, swap them. Now flag that you've done a swap, and you just keep going until the list is sorted. And how will you know the list is sorted? You'll know the list is sorted when you didn't need to swap anything. So it's very inefficient because it just keeps comparing and swapping items again and again and again. And the maximum distance an item can move to be closer to its correct position is 1 at each step. With selection sort and insertion sort, they can move quite a large part of the way to being in their correct position. But in bubble sort, they can at most move 1 hop. So even though they have comparatively the same big O of n squared performance, bubble sort will tend to be at the worst side of that performance most of the time. Whereas sometimes the other ones will perform quite well, but they will not. One case where bubble sort does fine, though, is on a sort list that's almost entirely sorted with a few items in just one place off of wrong, or if the list is completely sorted, it just tests to see if it's sorted and then returns. So in that sense, it does have 1 or 2 rare cases where it performs okay, but we're again always looking at the worst case performance. So bubble sort is not a good one. Quicksort is the sorting algorithm that's often used, or a variant of it is used in your libraries. It's a little bit more complicated, but basically what you do is you pick a position somewhere in the list called the pivot position. Then anything, if the list is sorted, anything that's less than the pivot must be to the left of it, and everything that's to the right of the pivot must be greater than it. So what you do is you pick your pivot, move everything so that they're on the right side of the lists, and then pick new pivots halfway between those sublists, and repeat the process. Then pick new pivots halfway between each of those sublists, again, recursively, again and again and again. So this basically does that. It just repeatedly sorts the sublists so that they're at the correct side of the pivot value, and then combines them together. So quicksort of the lesser list plus all the values that are the same plus quicksort of the greater list will give you the overall sorted thing. So being recursive, it uses memory up, same complexity class as merge sort. There are special variants of quicksort that are more memory efficient, which is obviously what a library would use, but the basic one is similar sort of memory usage to something like merge sort. What's the sorting you should actually use in real life when you're programming is not to implement any of these yourself, because then you're just going to make a mistake, is to use the built-in sorting algorithm inside C++. Let me just see, I'm getting a notification. Yeah, time's up. Okay, so we will finish off. There's only a little bit left, but all the important stuff, to be honest, there's not really much point. We'll take a look. We've done linear search already. It's big O of n. We'll take a look at binary search tomorrow, but then we're done, and we can do some revision after that. So thank you very much, ladies and gentlemen. Attendance code is last one. I don't think there will be attendance codes for the remaining lectures because they will just be revision. So this is the attendance code for today. Okay, so thanks a lot. See you for the revision. We will be uploading stuff on the SIG test. Where should the declaration have been submitted? Yes, no, upload it with everything else. If you're confused, just email the honesty declaration to me. It's fine. You know, not too worried about that. Okay, but thank you very much. I'm going to end the recording now. Yes, there will be tutorials, and we'll be doing past papers in the tutorials, and we'll be doing past papers in the classes as well. So yes, there will still be tutorials, except on Wednesday, which is Projects Day. There's nothing happening in the Academy on Projects Day, apart from Projects Day. Okay, all right. Ending the recording now. Have a good afternoon. See you later.